Hello and welcome. So we are going to continue our discussion on SPARQL. In the last two lectures on SPARQL, we have talked about different graph patterns. Basically, to say the basic graph pattern, the optional graph pattern, the negated graph pattern. Then we talked about the union graph pattern. Then finally, we talked about the graph pattern. Right. So today we'll start talking about another very interesting construct when we talk about the connection between two nodes in a graph, right? So before this, we were really talking about whether there is a triple existing in the knowledge base or not, and we have tried to design very complex queries by involving multiple triples, right? So here we will focus on the properties that we can see in as the labels of the edges in the graph. So if you take this graph as example, so Alice knows y1, and y1 has got name to be name 1, right? And then you have this y1 knows y2, y2 has got name to be name 1, and y2 knows y3, and y3 has nickname to be name 3. So you can think this to be a very small social network, right, where one person knows another person, right? So if you look at this graph, so this graph, if you take two nodes like say Alice and say y2, so these two nodes are connected via two edges, right? So these two edges, if you connect, so it is a kind of chain of the nodes connected via some properties, right? And this chain of properties are called the property paths, right? So this property path is nothing but a chain of properties, right? And what does this chain consider? This chain considers the connection between two nodes in the graph. So inside this you may have multiple other nodes, and finally you reach this particular target node, right? So this property path is basically a possible path from one node to another node in an RDF graph, right? So this is the definition of a property path, right? So now we will see that there might be very interesting patterns that we might want to require to present or represent various complex information need, right? So for example, let us start with a very relatively simple one, like say if someone has got if name to be a name, that will be the name of the person, or if a nickname, then that particular name will be also the name of the person. So there is an or condition, right? So if name or if nick, right? So either of this, if this is satisfied, then you connect two entities in the graph, right? So basically we are talking about alternatives. So you have say x and say you have y, right? And you connect x with y FOAF name, or if you have a connection like this FOAF nick, then both the cases y will be a possible output for this name, right? So y would be a possible, I will not say this to be variables, so these are concrete items. So you can think of this person 1 and say name 1, right? So depending on whether you have person 1 name n1, in that case also n1 would be one possible binding of the variable name, or if you have something like person 1 has got FOF nick to be n1, then also n1 would be a possible binding for name, right? So we are presenting one or condition. So the path either contain this or contain this, right? So you can see that this particular name one would be the output for this pattern, right? And this would also be an output because y2 has got FOF name to be name2, right? So we will be having output like y1 name1, then y2 name2, and of course y3 name3, right? Now let us take another example. So the same social network, but here we are trying to say that uh, the friend of Alice at distance 2, right? So what I'm trying to say, you have Alice, and Alice is a friend of someone or knows someone, followed by that person knows someone else, right? And that person has got FOF, I'm just write F, FOF name is equal to say name, right? So you're trying to look for these kind of patterns. So whenever you see a forward slash like this, so that means there should be one edge named as FOF knows, then followed by another edge named as knows, and then followed by this name, right? So this particular syntax is really representing this kind of patterns of path, right? So this is basically saying the friend of Alice at distance 2. So let us see what which are the entities that will be kind of instance of this particular variable or binding for this variable, right? So Alice is connected to y1 via nodes, one path, one property, and then followed by FOF name. So this cannot be one output because it is having only one FOF nodes, right? Then if y1 is connected to y2 with FOAF nodes, right? And if that is there, so this is one possible case. So we are up to this point, and then finally we can see that there is a name property following y2 and this connects to name2. So we know that this would be one output, right? So these four nodes are kind of affected if we apply this pattern. But if you look at this path, so we are having another FOF nodes, which is not really specified in my path pattern. So Y3 would not be one output, or the name of Y3 would not be one, will not be one output, right? Now we can extend this further, like say, friend of Alice at distance 2, 3, right? So friend of Alice at distance or distant 3 friend of Alice, right? So distance 3 friend of Alice, right? So here you can see that this particular node will be selected, right? Any other nodes? No, this is not going to be selected because we are coming to uh, mm, the count of 4 for nodes, right? So in this case, this particular name will be at the output stream, right? Now you can keep on doing this by adding more and more nodes. But if you want to represent something like, say, I will designate someone to be Alice's friend if the person is connected to Alice with a path which is having length greater than 1, greater than equal to 1, right? So what I'm saying, so I'll designate someone to be Alice's friend. So someone say X to be Alice's friend if Alice is connected to X, say via one nose path or two nose path or three nose path, so on and so forth, right? So if we follow this, so this is the proper syntax to represent that we have a repetition of nose for one and more than ones, right? So we have a repetition of nose relation in the chain for one or more than one, right? So in that specification, so what are the kind of nodes that we will be getting as output? So you can see that name 1 will be our output, name 2 will be our output, name 3 will be our output, of course, and name 4 will be output. So everyone you can see they will be coming to the output stream, right? So I will like you to look at this part. So here we are specifying a pattern of the path or a regular expression over the path sequence, right? So we can express this kind of regular expression over the path sequence to extract many complex relationships between the nodes, right? And that's why these property paths are very important while we are querying the RDF databases, right? So there is another interesting construct while we talk about the property path, so which is called the inverse property path. So let's say you have a path between two nodes. So for example, we have here, so X knows Y, right? So whenever we are saying that we are inverting this property path, so that means we are exchanging the object and the subject position, right? So if we do that, you see the directionality is also changing. So if we just swap the objects and the respective subjects, the directionality is getting changed, right? And that is basically one inverse relationship of the given relationship. And this inverse relationship is represented by one caret at the beginning and then followed by the relation name, right? Or property name. Now, what kind of use this kind of reversal of the path we can have? So let us have a look at one example, right? So the example says that persons, I need to find the persons who know the person known by X. So what do you mean by that? So we know that X is the person. So let us assume that. And X knows some other person, right? And this person is also known by Y1, Y2, Y3. So if that is so, then our output would be Y1, Y2 and Y3. And this is basically modeling the persons having common friends. So this X, Y1, Y2 and Y3, they are having a common friend here. So let us name it to be Z. So Z is a common friend of X, Y1, Y2 and Y3. So what we want to have as output for given X. So for given X, I want as output Y1, Y2 and Y3. So let us see how could we achieve this, right? So basically we will be doing path graph traversal. So we start at X, then we move to Z, right? So let us move to Z. So let us move to Z. Now the next question is, how do we reach Y1, Y2 and Y3? If we cannot reach Y1, Y2, Y3, we cannot have them as our output, right? So what is the trick that we are playing here? We are basically reversing all the paths. So we are reversing all the paths. So if we have like Z, Y1 knows Z, we also add another path here which says that caret knows. I'm not writing FOF, right? So we are reversing the path and we are doing this for the other edges as well, right? Now, you can see if we have this kind of setting, now I can come from X to Z and follow the path, right? So the traversal is possible now. So that's why we are adding these reverse edges, right? So how do we represent this? So we represent this like so. Nose, we start with nose. So we have X, nose, and then followed by nose inverse, right? So this path, so we are writing nose inverse. And whatever element is connected to X in that path pattern, so let us name it to be say question mark Y, that will be our output. And you can see that Y1, Y2 and Y3, they are becoming our output. So we can basically specify this path pattern as X FOAF nose forward slash then caret FOAF nose Y, right? But this trick is having a problem, right? What kind of problem it is having? So as we are adding one reverse node or reverse edge for every edge, we should do this for this edge also, right? So we are adding one reverse edge here. Now if you do that, we start from X, go to Z, and from Z we will be following this path to come back to X, and that means we will be having X also as the answer, and which we really don't want to have. So in that case, we know that we can use one filter condition just by saying that your X, the source, and the destination, which is Y, they should not be the same or equal, right? So you see that we can make use of this reverse path pattern in various cases, right? Now, this is yet another toy example, which is basically you can say a Twitter following network. Twitter following network. So in this network, what is there? So basically, a person follows another person. So if P1 person 1 follows person 3, we have one edge from person 1 to person 3, and we can see that there is a set of connections between a subset of the pair of nodes. Not all of them are connected, but you have a subset, right? Now here we will be playing with different path patterns that we have seen earlier and try to see what kind of output we can observe, right? So if you have these path pattern, for example, persons who follow person 5 with any length greater than equal to 1, right? So basically, uh, these person 8 and person 9, they are following person 5 at distance 1. Person 3 is following person 5 with distance 1. Person 6 is following person 5 with distance 2, right? So these all will become the follower of person 5, right? According to the definition that we have encoded using this path pattern. So let us see what are the nodes that will be coming as the output. So these are the nodes that will be coming as output or binding for this P, right? So let us run this query. So we have one turtle representation of this network in a turtle file, and we'll be running this query which encodes this particular path pattern, right? So let us have a look at the data. Um, So you can see the data. So this is the turtle representation of the graph that we have seen. So we are saying that person 1 follows person 3, then person 2 follows person 6, so on and so forth, right? And let us have a look at the query. So yeah. So the query says that you want to find the persons who are following person 5 with any path length which is greater than equal to 1, right? So let me run this query. So you have 14a, 14a, 14 dot turtle. Now if you execute this query, okay, I need to mention data. So there we have encoded the pattern that you have seen. Now you can see that we expected one person 2, but we are having a repeated entry of person 2 in the output, right? So let us see why that is happening, right? So the reason that this is happening is that you have multiple paths from person 5 to person 2. So for example, if you follow this path, so this is one case, then you follow this path, this is another case. So basically you are having 4 such paths, and as we are having 4 such paths, we are having 4 output uh, as person 2, right? So we have repetition of 4 times of person 2, right? So you can see that as many number of paths you'll be having between person 2 and person 5, that many output of person 2 will be having in the output stream, right? Now, can I ask a question like which persons also follow the persons that person 6 follows? So this is basically following the common friend kind of example, right? So we can write it very simply, right? So we are using the same path pattern to see whether this query can be satisfied or not. So you can see the output here would be person 7. Now we have provided example for few of these path patterns, but let us have a look at what are the other path patterns that we can have, right? So these we have already seen that you have a sequence, right? So you start with one node with say path 1, then you have another node, and these two nodes are connected via path 2, right? So it's a sequence. Now, reverse of path you have already seen. So you have these things. So I should always mention this directionality, right? So you have a path 1. So you can establish another path like caret path 1, right? Path 1 or path 2. So you have two nodes. So one path is having path 1 label as path 1, and the other path is having the label as path 2, right? Path 1 star means that this path 1 can may not occur, or it may occur uh, one or more than once, right? So it occurs either 0 times or repeated more times, right? One path. Path plus means that this path is repeated one or more than one times, right? So if you have something like this is also satisfied, or if you have something like this, you have path 1 then another path 1, this is also satisfied, and this can go on forever, right? Now if you have like path 1 mn, so that means if you have two nodes and you have a chain here, you have a chain here of say path 1. So every path, every property is path 1, right? Now you should have at least m repetitions, but no more than n repetitions, right? So the number of repetition would be greater than equal to m. The number of intermediate paths or repetitions will be greater than equal to m, but less than, so I'm just saying number of path 1 should be less than equal to n, right? Now, if you have only one number, that means you have exactly one occurrence of path 1. And if you have the second argument missing, that means you have at least m occurrences of path 1, and the other part is you have at most n occurrences of path 1, right? So you can see you can make use of it in different scenarios. So we have given one example of the social network where you can define the friendship relationship between two nodes if they satisfy certain criteria, but you can use this to define many other interesting properties in the graph for different scenarios. Now, you can observe this to happen in DBpedia in reality. So here we are trying to find out the movies that have common actors. So it is again kind of example of the common friend, right? So here we are saying that movie 1 has got type to be film. So we are just considering the films, and it is starring some person. So you have movie 1, it is starring say actor 1, right? We can name it anonymous, so you may not have any name because we are not naming it. So this is basically one blank note, right? And you have something, it is followed by this path, this property in the path is followed by the reverse of starring, right? And what you have here, you have movie 2, right? And these two movies are connected via this actor. So these two movies are having common actor. So you can establish a relation like this, like say has common actor, right? Now, in many cases, you will see that the set of results or the list of results you are getting, there might be repetitions, and these repetitions may be annoying, and they might give you wrong calculations, right? So you want your output in many cases to be a set, not a kind of bag where you have repetitions of the same entity, right? So for that, we'll be using this keyword distinct, right? So what we are doing in this query, so we are retrieving the set of company names that have founder and product. So this is a query that we have seen earlier. So basically, we are considering the company which are software companies, uh, and optionally, if they have founders and the products, we want just the name of the company, right? So let us run this query in DBpedia. So, when we let us first select the query. So yes, so this query is already selected. So let's copy this and put it in this. Okay. So let us first remove this distinct keyword. So if we remove this distinct keyword and then fire this query, what we can see that we have got repetition of Microsoft many a times. We have repetition of say symbolics many a times. So this is what we don't want.